Greetings, ladies and gentlemen. My name is Ryan Shazani, and welcome back to another physics video. In today's video, I'll be showing you why the gravitational force inside a spherical shell is zero. So first, let's take a look at this diagram. We have a spherical shell of mass ms, and we have an object inside the spherical hollow shell mx. And the distance between the center of the spherical shell and the object is denoted by small letter r. And the radius of this spherical shell is capital R. Now, to tackle this question, let's start by writing down the equations first. So we want to find why the gravitational force inside is zero, right? So by ms on mx. So we can say that F is equals to negative du over dr, where du, or where u, is the gravitational potential energy, and dr, or r, is just the distance between mx and ms. Yeah. We also can say that u is equals to negative g m s mx over r. So how are we going to tackle this question? We can actually find out by finding the expression of the gravitational potential energy due to one ring, and then we can integrate that to make that ring expand such that it makes a hollow sphere. What do I mean by rings? So if I were to slice this spherical hollow shell into an infinite number, I can actually visualize it to be an infinite number of rings, right? And from this, I can see that if I were to make a ring like this, so this ring that I've just drawn is the side view of this ring in red. So imagine this model paper ball to be a spherical hollow shell, and I've drawn a red circle here. And this red circle, if you to look from the side, is just this right here. This is the side view of this red circle. So I hope you can visualize that. And from there, I can see that the distance between the object and this ring is denoted by L, and there's an angle here, theta. Okay, so what I'm going to do is I'm going to find the expression of the gravitational potential energy due to this ring. This is of course the side view, or due to this ring right here, and then I can integrate it from the small ring right here, expand it all the way for the spherical hollow shell. So let's start by writing some equations. I can say that du is equals to negative g m x dm over r. And what does dm mean? So dm actually refers to the mass of one ring, and mass of one ring can just be found by saying that you can take the ms, or the mass of the whole spherical shell, and the ratio of the surface area of the ring to the surface area of the spherical hollow shell. Why am I taking the surface area? Because it is a spherical hollow shell, therefore it's infinitely thin, right? So 4 pi r squared, and the surface area of the surface area of the ring is denoted by the circumference. So the circumference is 2 pi r squared, right? The radius. But in this case, the radius of this ring is actually r sine theta. Yeah? So 2 pi r sine theta. And the thickness, which is just the infinitesimal arc length, is just r d theta. So if I were to simplify this, I'll get the m to be equals to ms sine theta d theta over 2. Then I can write down du equals to the integral of negative g mx ms sine theta d theta over 2 L. Yeah? Why is this L? Because we're trying to find, because this denotes the distance between the object and the mass that I'm trying to find the gravitational potential energy that is being caused by, and that is the ring. So the distance between the object and the ring is L. Therefore, this is L and not R. But the thing is, if you look at this, okay, this is from 0 to pi, yeah? But if you take a look at this expression, there are two changing variables. First is theta. Theta is always changing. As I increase the ring, or if I move the ring to here, then theta will increase, right? And I also have L, the distance between the object and the ring itself. It always changes. Therefore, I have to find a way to make this to be into what just based on one variable. What I can do is actually I can see that if I were to draw this diagram again, so this is R and this L and this theta, I can see that this L squared is equals to R squared plus R squared minus 2RR cosine theta. This is based on cosine rule. And if I were to differentiate this, I'll get 2L dL equals to 2RR sine theta d theta. And you can see that I have sine theta, d theta, and 2L, and therefore I can make the subject for sine theta d theta over 2L is just equals to dL over 2RR. And with this, I can substitute it into this, and I'll get du is equals to the integral negative g mx ms, and substitute sine theta d theta over 2L to be dL over 2RR. Yeah? And what are the notations here? If you take a look, I'm trying to integrate from L, based on L, right, with respect to L, and the minimum distance is just this right here, and this is, so this length is R minus R, so from R minus R, so this is the minimum length, and to the maximum, which is just this right here, and this is R plus R, so plus R, and this is just equals to negative g mx ms over 2RR R plus R minus R plus R, and I'll get this to be negative g mx ms over 2 over R. Yeah. Okay. So we have the expression for du, and therefore we can see that du is equals to negative g m over R. Yeah? And to find f, you can say that f is equals to d over dr of negative g, or negative d over dr over g mm ms mx s mx r. But take a look at this. We are differentiating it with respect to small letter r, but we do not have small letter r inside this expression. This expression, or du, is, or u, is independent of small letter r. Therefore, I can say that this is equal to 0. And voila, we have shown that the force, or the gravitational force inside a spherical hollow shell, is 0. Alright, if this video was helpful to you, then make sure to subscribe to my channel, like the video, share the video, and all of that. Thank you for watching, and I'll see you in the next video. Goodbye.